Welcome everyone. This video will discuss about the concepts of the reflection of a uniform plane wave incident normally at the interface of two different mediums. As the topic suggests, we will cover the wave reflection only in lossless mediums. As we are discussing about uniform plane wave, so it is possible only for if the medium is lossless. Reflection of plane wave takes place when a plane wave from one medium meets a different medium. It is partly reflected and partly transmitted. The portion of the incident wave that is reflected or transmitted depends on the constitutive parameters sigma, mu, and epsilon. As we are assuming lossless medium, sigma will be 0. Assuming the incident plane wave is normal to the boundary between medium 1 and medium 2. So here the medium 1 is defined as z less than 0 and medium 2 is defined as z greater than 0 and the boundary is at z equal to 0. So here this black line is the boundary. Let's assume this is the z-axis. So this side will be z positive and this side z values are negative, and at the boundary or the interface between two mediums is z equal to 0. Now the wave that is coming from medium 1 and incidence 1, this boundary is called incident wave, and the part of the wave that get reflected back to the medium 1, that's called reflected wave, and the other part of the incident wave that is transmitted in medium 2, travel through medium 2, is called the transmitted wave. So now look the diagram here. The incident wave shown in the green and the reflected wave on the red and the transmitted wave in green. So incident wave in blue, reflected wave in red, and transmitted wave in green color. So if you look at the incident wave, it is propagating in positive z direction and the medium 1, and the reflected wave will propagate in negative z direction in medium 1, and the transmitted wave will propagate in positive z direction but in medium 2. So be careful here. Medium 1 has two waves, incident and reflected. One is in positive z direction and other one is opposite to that. That means negative z direction. Transmitted wave in medium 2. So in medium 2 we have only one wave that is propagating in positive z direction. And other point to mention here, the incident wave has the highest amplitude, then some part will be reflected and transmitted. So that if you add the amplitude, as you see here, we have three waves for electric field, and also we will have three waves for magnetic field. So in total we have six waves. As we need to work with six different types of wave simultaneously, so if we use six different equation or six different graphs, very difficult to handle with. So that's why we will use a very simple strategy for representing the waves. In the look at the expression here, mathematical expression of a uniform plane wave E propagating in positive z-axis and polarized along x-axis. So here the mathematical expression, the amplitude, the E field polarized in x-axis and propagating in positive z-axis, if we want to find the corresponding magnetic field, we can use this expression and then solve this equation, substitute the E value here and solve this, you will get the magnetic field equation like this. Now, this is the expression for electric field and magnetic field equations. We can also represent the field graphically. So if you see it is a sinusoid graph propagating in z direction and varying in the x direction. Let's say this is E field. So the graphical and mathematical representation is little bit time consuming. So because we have to work with six different kind of equation or six different kind of graphs. So solving the reflection problems with this equation or this graph may be a little bit hard to represent them. That's why we are using a simple line diagram here. So the line diagram will show the information about the propagation direction and the polarization direction or variation. So you see the E field varies in x direction. So we are showing the direction vector like this. X is the vertical axis, Z in horizontal axis, and Y is pointing outward to on the screen. So that's pointing vertically outward. So now if we want to represent this E field equation with line diagram, we can do that showing the propagation direction in the z axis and the E field variation in x axis and the corresponding magnetic field that is propagating in z direction and varies in the y axis. So y axis we use dot, meaning that it is pointing outward or outward on the screen. Line diagram for the other equation, let's say we have equation like this. So this equation on this equation, so here if you assume the electric field expression like this, it is propagating in negative z direction and polarized in x-axis. So the simple line diagram of this corresponding expression will be like this. So it is E field varies in x and propagating in negative z direction. Similarly, the magnetic field here it is varying in y direction, but there is a negative sign here. So the magnitude of H is pointing inward to the screen. So you can use a cross here that is the negative, representing the negative, and it is propagating in negative z-axis. So if we have a electric field magnitude negative E, we have to put it in the downward direction. So if E naught is negative, so then this diagram E should be shown on the negative direction. So this is how we can represent uniform plane wave with line diagram, and we use this concept. So look at the diagram here. It is showing the concepts of normal incident of electromagnetic wave on perfect dielectric interface. Let's say we have two dielectrics. One is medium 1 and another dielectric is medium 2. The constants of the medium 1 is mu 1 epsilon 1 eta 1 and mu 2 epsilon 2 eta 2 for medium 2. We are showing the directions like AZ, AX and AY. So now let us assume the electric field, incident electric field is polarized in x-axis and propagating in z direction. So we show it here like this. You also can show this way too. So this way showing it is polarized in x-axis and propagating in z direction. And the magnetic incident wave. So the magnetic field incident, magnetic field that can be shown either this way. So this is in positive z direction and polarized or varies in y-axis. So you can show it this way or this way, simple line diagram. The reflected electric field will be polarized in x-axis, propagating in negative z direction, or the simple diagram like this. So if it is varies this way, propagating here this way. And magnetic field, reflected magnetic field, that will be propagating in negative z-axis, but varies in negative y direction. And it is worth mentioning that if E field for incident and reflected is varies or polarized in the same direction, then magnetic field will varies in opposite direction. So, for example, the incident magnetic field that varies in positive y, but reflected magnetic field will vary in negative y direction, because the electric field we are assuming they are varying in the positive x direction. Now for the medium 2, the transmitted electric field diagram is here. So transmitted electric field propagating in z direction and polarized in x-axis. You can show with this diagram or this one. So you know you don't need to show in both diagrams. Either show this way or this way. And for magnetic field, we show the magnetic field propagating in z-axis and varies in the positive y direction. So this is how we can show the boundary systems for electromagnetic wave. So always you need to keep in mind that your boundary system will like this. It will have two mediums, medium 1 and medium 2, and on the interface, and we have 6 waves total. So to on electric field incident wave, magnetic field incident wave, electric field reflected wave, magnetic field reflected wave, electric field transmitted wave, and magnetic field transmitted wave. So there are 6 waves. So you have to either use 6 line diagram or 6 this simple diagram. So 4 in medium 1 and 2 in medium 2. So now incident, reflected, and transmitted wave. So here let us assume we have an incident wave for electric field. We use Es in frequency domain and the I is for incident. So ESI, and it has a magnitude E0I, and this is the phase constant beta 0 e to the power j beta 1 z ax. So ax is the polarization direction, z is the propagation direction, and I is for incident wave. Similarly, the magnetic field, we can find this using this equation and then replace E0I over eta I as H0I. This is the magnetic field. Now for reflected wave, so assume the same polarization to the incident wave. So I am assuming the electric field got the same polarization. So ESR will be E0R e to the power j beta 1 z AX. So here you see we are assuming same polarization. So AX is the same, this sign is the positive. Here you see the reflected wave propagates in the opposite direction to the incident wave. So as the incident wave propagating in negative, positive z direction, so the reflected wave will be negative z direction. So here it is called z beta 1 z. Be careful. The reflected wave always will be opposite direction of the incident wave. And SSR, which for reflected wave, we are getting this the expression like this. So it is has a negative sign here. So we got a negative sign here, meaning that the magnetic field variation will be opposite to the incident wave. So here we had positive, but in this case we got a negative. So that it will be polarized, varies in the negative direction, opposite direction to the incident wave, but and also propagate in the uh, negative z direction. This is the transmitted wave. So transmitted wave is this magnitude propagating in positive z direction and polarized in the same way to the incident wave. Transmitted magnetic field, that is the varies in the same way to the incident wave. The only difference for transmitted wave, you see, we use the suffix t, and other thing to be careful about. So this is in medium 2, beta 2. We are using beta 2 here because the transmitted wave in medium 2, and medium 2 has phase constant beta 2. Medium 1 has phase constant beta 1, that is omega mu 1 epsilon naught, and beta 2 omega mu 2 epsilon 2, and the impedance is eta 1 mu 1 epsilon 1 and eta 2 for medium 2 mu 2 epsilon 2. So here you see I use eta 2, and for reflected wave I use eta 1, transmitted wave I use eta 1, because this incident and reflected waves are in medium 1, but the transmitted one will be in medium 2. So for transmitted waves, be careful about the suffix 2. So you have to take the electrical characteristics of medium 2. But for incident and reflected wave, you have to take the medium electrical characteristics of medium 1. And at the same time, for incident wave, it will propagate if it is propagated in positive z-axis, the reflected one will be negative z-axis. So that will be opposite. So incident reflected waves got the opposite propagation direction, but same electrical constants like beta 1, eta 1, they are same because this is in medium 1. But transmitted wave, it is in medium 2, so you have to take beta 2, eta 2, but that will propagate in positive z axis. So here E0R, E0T can be expressed in terms of E0I. So this is what we are basically looking for, because in this case you see we have a lot of things to know. One is beta 1, eta 1, E0I, then E0R, E0T. But E0I will be partly reflected and partly transmitted. So there is a relation between E0I and E0R and E0T. So we need to find out what is the relation between E0R to E0I and E0T to E0I. So we will be finding the expressions for the relationship between the incident and reflected wave and incident and transmitted wave. So now if you look at the medium one, you will find two fields, two electric fields and two magnetic fields. One is the incident electric field and another is the reflected one. So now if we add incident and reflected electric field together, so that is called the total electric field in medium 1. So in medium 1, we use the suffix 1 here, so in bracket. So this is for ES1, that means total field. So if you see a notation like this in 1 in parenthesis, so that is called the total field in medium 1. So that is the sum of incident wave and reflected wave. We know the expression for incident wave and also the reflected wave. And magnetic field, the total magnetic field in medium 1 is this one. SSI, SSR, this is the expression. Now total field in medium 2. Medium 2 got only the transmitted wave. So the total field is the same of the transmitted wave. So you can write E0T e to the power beta 2z, and SS2 is S0T e to the power j beta z. So at total field at the interface at z equal to 0. So at z equal to 0 minus, that means at the interface, but in uh, in relation to the medium 1. So in medium 1 we'll get E0I. So I am putting z equal to 0 in this equation. So we are putting z equal to 0, but relating to the medium 1. So we got E0I and T0R. If you put z equal to 0 in this expression, so that is on the surface but closer to the medium 2, so you'll get E0T. Similarly, for magnetic field, you will get A0I, A0R, and for second medium, you'll get A0, 0 plus is A0T. So at the interface, you know the boundary conditions that we have learned, the tangential component for E and H field must be continuous. Since the waves are transverse, E field and H field are entirely tangential. So you see the wave polarized in X or Y axis, propagated in Z axis. So both X or Y direction is not tangential to the interface, parallel to the interface, right? X is parallel to the boundary, also Y is parallel to the boundary. So we see the electric field and magnetic field both are parallel to the boundary. They are tangential to the boundary. So we can write that E1t equal to E2t. So E1t is this one. So E1t is this one and E2t is this one. So E1t is E0I plus E0R and E2t is E0t. So we got a relation that the E0I plus E0R is equal to E0t and H0I plus H0R equal to H0t. So we got an expression like this, that electric field magnitude at the boundary for incident wave, for the reflected wave. If you sum them, you will get the transmitted wave. Similarly, if you add the magnetic field amplitude of the magnetic field at the boundary of medium 1 will be equal to the medium 2, magnetic field in medium 2 at the boundary. Now reflection and transmission coefficient. So we can find the coefficient, how much will be reflected and how much signal will be transmitted. So the reflection coefficient is the uppercase gamma and the transmission coefficient is tau. So we use gamma, uppercase gamma for reflection coefficient and tau for transmission coefficient. And always we find the reflection, we can find the reflection and transmission coefficient at the interface. So reflection and transmission coefficient at the interface z equal to 0 can be defined as that. At z equal to 0, the reflection coefficient is E0R over E0I and the transmitted coefficient is E0T over E0I. So if you want to define the reflection coefficient, that is the magnitude of reflected electric field. So that is the ratio of magnitude of reflected electric field to the magnitude of incident electric field at the boundary. It's called the reflection coefficient. And transmission coefficient is the ratio amplitude of transmitted electric field to the amplitude of incident electric field at the boundary. And A0I, H0R equal to H0T. So now H0 basically E0 over eta 1, H0R will be E0R over eta 1 and A0T will be E0T over eta 2. Now if you multiply the entire equation with eta 1, we'll get E0I minus E0R equal to eta 1 minus eta 2 times E0T. So now E0I, E0R and divided by E0T. So E0T is basically E0I plus E0R that we got here. So we replace E0T with E0I plus E0R. And this one is E0I minus E0R. And we write it like eta 2 minus eta 1. So now if you Simplify this, you will get 2E0R over 2E0I is eta 2 minus eta 1, eta 2 plus eta 1. Just we are adding uh, denominator. We are subtracting denominator from here, from the numerator, and also adding numerator with the denominator. So here we got the reflection coefficient is E0R over E0I equal to eta 2 minus eta 1, eta 2 plus eta 1. So this is very important formula to know, eta 2 minus eta 1, eta 2 plus eta 1. So this is how we can calculate the reflection. So reflection is basically depends on the wave impedance of both medium. If the N2 is higher than N1, you will get positive reflection. If N2 is lower than N1, then you will get negative reflection. And depending on this value, positive to negative, you can find the polarization of incident and reflected wave in comparison. Now, if you take this relationship here and divide the entire equation with E0I, so then E0I, 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 and E0I, this will be 1, and this is reflection, and this is the transmission. So transmission is equal to 1 plus reflection. So this is simple expression. You can know this this formula. Once you know the reflection coefficient, you can find the transmission coefficient. 1 plus reflection will be transmission. Or if you substitute eta 2 minus eta 1, eta 2 plus eta 1, here you can get the transmission equal to 2 eta 2 over eta 2 plus eta 1. Now we can write the total field equation for medium 1. You see the total equation, total electric field was E0I e to the power z beta 1 ZAX plus the reflected one E0R E beta 1 Z. Now we can take E0I as a quant factor, so it will be E0 e to the power z beta 1 ZAX. Now here will be E0R over E0I, that is equal to the reflection. So now you see we can easily remove E0R from the expression by introducing the reflection constant. So just if you know the amplitude of incident electric field, that will be enough to get the A wave, incident wave, reflected wave, or also the transmitted wave, because there is a relation between transmitted and incident wave. So similarly, the total field in magnetic field can be written like E0I eta 1 is equal to this. So be careful here, for magnetic field we got negative, but for electric field we are getting positive. So if reflection is positive, this value will be positive. But for magnetic field, this value will be negative, because if the electric field has the same polarization for incident and reflected wave, then the magnetic field will be opposite. For example, if the magnetic field for incident wave is varies in positive y direction, then the reflected one will be varying in negative y direction. So this is very important concept to know, that if you have positive for the total electric field, then total magnetic field must be negative. If you have negative for total electric field, then magnetic field will be positive. So this is very important things to know. Similarly, for medium 2, we can write the total field is E0T, this one, or the transmitted field, that can be written like tau E0I, this one. And for magnetic field, we can write tau E0I over eta 2, this one. So you see, we didn't write tau E0I because there is no relationship for magnetic field. The relationship only for electric field. because magnetic field is calculating for magnetic field with considering the impedance. So if you write H0I tau H0I times this for H T, the transmitted magnetic field cannot be obtained this way. You cannot write tau H0I is equal to H H0T. You cannot say that because the transmission coefficient formula is only for electric field, not for magnetic field. Similarly, the reflection also only for electric field, not for magnetic field. But for reflection, if you take H0R over H0I, H0R over H0I equal to gamma, that will be wrong. Gamma will be negative H0R over H0I. Want to find reflection using magnetic field? Be careful that gamma will be H0 negative H0R over H0I. But there is no formula for transmission coefficient using magnetic field. So we cannot use magnetic field intensity to find the transmission coefficient. Now the incident power. So if you want to find the electromagnetic power, time average power, you can use the formula. This is the incident electric field and incident magnetic field conjugate. So if the electric field got this expression and magnetic field will get this equation, the conjugate of magnetic field will be positive J negative J transformed to positive J, and then we'll get the expression like this. So you see 1 over eta 1 is 0 I squared ax plus ay across ay, so az. So you see here the time average power density or time average Poynting vector PAVI for incident wave can be obtained this way. That will be 1 over 2 eta 1 E0 I square AZ. So we see the direction is AZ, meaning that the power is transmitted to the Z direction, or power is flowing to the Z. As wave is propagating in Z axis, so power must be propagated to the Z axis. Now for reflected power, the time average power for the reflected wave, you can find it like this way. SSR, ESR times SSR conjugate, and the final formula will be 1 over negative 2 eta 1 E0 R square AZ. So here we got a negative sign because now the power will be transmitted in positive Z direction, negative Z direction. So we got a negative at AZ, meaning that power is flowing in the negative Z direction. Now the ratio of the reflected to incident power. So you got the incident power expression here and the reflected power expression this. Now if you take PR over PI, you will get this. So gamma square. So at the interface, you will get PR over PI equal to gamma square. So if you know the gamma, you can find the ratio to the reflected and incident power. So once you find the incident power, you can find reflected power. Or also you can find, once you know the reflected power, you can find incident power by using this formula. Or if power is known, you can find the reflection coefficient. Now, the transmitted power, for time average transmitted power, you can use the transmitted electric field and transmitted magnetic field conjugate, and you will come up with this equation. Now the transmitted power is Pt over Pi, you get this. And then Pt over Pi will be tau square eta 2 minus eta 1. So now if you look at, recall the previous slide, you see PR over Pi, the reflected power over the incident power was gamma square, but transmitted and uh, incident power ratio is not tau square. It is tau square, but there is a factor eta 1 over eta 2. So sometimes a student Students make mistake like this. They write it simply tau square, but be careful. For incident reflected power, both happen in same medium, but for incident and transmitted power, they are not happening in the same medium. Incident in medium 1 and transmitted in medium 2. That's why the formula is a little bit different in case of the reflected power. Sometimes we might ask you to find the percentage of reflected power. The formula is this: reflection squared times 100, and percentage of transmitted power is. So we can find how much power will be reflected and how much power will be transmitted. For example, if the reflection coefficient is 0.5, meaning that 25% power will be reflected back and 75% power will be transmitted. Now you see we have two waves in medium 1. So these two waves, one is the incident and another is reflected waves. So we have two waves with same frequency but traveling in opposite directions. They might superimpose with one another. So the result of the interference of two waves in medium 1 is a new wave pattern known as a standing wave pattern. So if you have two opposite traveling waves with same frequency combined together to produce a new wave called standing wave. The standing waves are produced whenever two waves of identical frequency interfere with one another while traveling in opposite directions along the same medium. So you see when we see the interference here, you have some nodes and some antinodes here. So these are the nodes and these are the antinodes. So standing waves is something confined in this area. So this wave is not cannot travel or carry any power. So this is confined in this medium. Perfect dielectric and perfect conductor interface. So let's say we have a perfect dielectric and perfect conductor. So perfect dielectric sigma will be 0 and we have mu1 epsilon 1. For perfect conductor sigma will be infinity and it might have mu2 and epsilon 2. Now the beta will be j omega mu1 epsilon 1 and the wave impedance will be mu1 over epsilon 1, that is eta. And for perfect conductor we find eta 2 is mu1 epsilon e2 and mu2. If this value will be super very higher than 1, so you can write it like uh, omega sigma omega mu, and sigma is infinity, so something over infinity leads to 0. So the impedance of conductor will be 0, and it is very obvious that if you have a conducting wire, the power loss is 0, so the resistance or impedance will be 0. So that is 0 here. Now the reflection coefficient, we can find eta 2 minus eta 1, eta 2 plus eta 1, eta 2 is 0, so you get minus 1. And the transmission coefficient is 0, meaning that 100% power will be reflected back and nothing will be transmitted. And this is very obvious that if you have a perfect dielectric and good conductor, then no field can pass through the conductor, right? As you know, if the conductor is thick enough, so no signal can pass through the conductor or penetrate to the conductor. So all the signals will be reflected back. That's why we got reflection equal to -1 and transmission is 0. So now if you want to find the reflected wave amplitude, that will be reflection times E0I. Reflection is -1, so it will be negative E0I. And transmitted electric field will be 0. So assume if we have an incident wave like this, ESI equal to E0I to the power this, then the incident magnetic field will be E0I over eta 0Z AOI. So this is the magnetic field. Therefore, the reflected electric field will be reflection times this E0I. Reflection is -1, so that will be -1 this. And the reflected H field is SSR E0R over eta. Then you can find this. So look at this here. Electric field has a positive, magnetic field incident has a positive. Electric field reflected got negative, but magnetic field reflected got positive. So be always be careful about this. So if the electric reflected electric field polarization is opposite to the magnetic field, then the reflected magnetic field and the incident magnetic field will have the same variation direction. So both will be positive AY. You see here you got positive AY, this is also positive Y because electric field for incident wave is positive X but the reflected wave is negative X. Now the total electric field you can add the incident and the reflected. You will get this one. This is the total electric field wave. And similarly, this is the total magnetic field wave. So now the standing waves in E and H field. So the total electric field wave is this one. So now you see E0I and this is e to the power negative z beta z. So you can write it cosine beta z minus j sine beta z. And this is positive z beta z. So it will be cosine beta z and we have minus n here, so j minus beta z ax. Now this cosine will be cancelled out, so you have 2 E0I j sine beta z. So ES1 is 2 E0I j, j is like the sine function, so you can write sine omega t and sine beta z. So now the total field has a sine wave and this. Now you see here the time function and the phase constant, they are separate. So this wave is not the traveling wave. Traveling wave has a omega t plus or minus beta z. But here omega t is a separate term and beta z is a separate term. So this type of wave is called a Stirling wave. So you have a sine function with respect to time, another sine function with respect to the space. So they are Stirling wave. Now, if you think about magnetic field, you will get the expression like this. Break this with cosine and sine, you will get this one. So this is the magnetic field expression. So here, E0I over eta is H0I. So if you plot the standing wave, here you can see the standing wave for different omega t. So if you take omega t is pi over 2, 3 pi over 2, pi over 6, 5 pi over 6, you will get the standing wave. So a standing wave is like particle are oscillating in this way, but it is not traveling. So the field is not carrying any energy. The standing wave for magnetic field, if you see the magnetic field, plot the magnetic field, you will get the standing wave like this. So it got some nodes, these are the nodes and these are the antinodes. Now the power in the standing wave. So you see we got the E field expression and the H field expression. So E field expression is E0I J sine beta Z and H field is E0I cosine beta Z. So now if you take the imaginary real part of this, but there is no real part. There is a z term, so z terms take to imaginary part. So there is no real part. So a real part will be 0. So that means there is no time average power. So a standing wave cannot carry power. Now, if you have two dielectrics, then dielectric 1 and dielectric 2 lossless. So you have 0 mu 1 epsilon 1, 0 mu 2 epsilon 2. So you can find beta 1 and eta 1, beta 2 and eta 2. This is the reflection coefficient, formula eta 2 minus eta 1, eta 2 plus eta 1. Transmission coefficient is 1 plus tau. the how to find the amplitude of reflected and transmitted wave. This is the formula for finding reflected wave and transmitted wave. So if the incident wave is this, then the incident magnetic field will be this. The reflected magnetic electric field is this equation. Reflected magnetic field has this equation. The transmitted electric field has this equation. Transmitted magnetic field is here. The total electric field is the incident plus reflected, and total magnetic field is the incident plus reflected. So this is the parameters or wave equations we might ask you to find here. So one is the reflection coefficient, transmission coefficient, incident wave, reflected wave, transmitted wave, electric field and magnetic field. So now if the medium or impedance eta 2 is higher than eta 1, then gamma will be greater than 0 and tau is less than, sorry, greater than 1. So EST will be a positive here, but SS1 will be negative. But if eta 2 is smaller than eta 1, then gamma will be less than 0 and tau will be less than 1. So you will get negative here and positive here. So be careful here. So if the reflection is negative, you will get negative for E field, but positive for S field. But if reflection is positive, you got positive for E field, but negative for S field. So now the standing wave ratio, we need to find the standing wave ratio expression here. So to find the standing wave ratio, let's say we have a standing wave ratio is the maximum to minimum magnitude of frequency domain electric field or magnetic field. So you see ESI has the expression like this. So we can write E0I. Now we can find E0Z beta Z on plus gamma this. So the maximum electric field will be, so when the field will be maximum. So here this is the propagation term. So forget about this propagation term. Now we assume this is the magnitude here. This point up to this point is magnitude. So magnitude is E0I times 1 plus reflection times this. This is basically cosine function, right? Cosine function or sine function. So let's assume cosine function. So cosine varies from positive 1 and negative 1, between positive 1 and negative 1. So if we assume this is positive 1, you will get maximum value here. And if you assume this is negative, you will get minimum value. So ES1 will be maximum if 1 plus gamma, if E0I times 1 plus gamma. This is very obvious. If you add the amplitude of incident wave and reflected wave, you will get the maximum. But if you subtract the reflected wave from the incident wave, you will get the minimum. So ES1 max, ES1 minimum. Similarly, SS1, it has this expression. So SS max will be on eta E0I on plus gamma, and SS1 minimum will be 1 over eta E0I on minus gamma. So ESI maximum is the sum of incident magnitude plus reflected magnitude, and TSI minimum is the difference between incident and reflected magnitude. So now if you think about E0I is 150 to the power z beta z ax and E0R is negative 50 this. So what will be the standing wave ratio? The standing wave ratio will be ES1 max over ES1 minimum. So here the maximum will be 150 plus 50. So 150 plus 50 and minimum will be 150 minus 50. 150 minus 50. So we're just taking the amplitude of E0I and amplitude of E0R, amplitude of E0I minus amplitude of E0R. So 150 plus 50. So if we give both of them positive, we will have the same number, right? Because 150, we are taking the number here, 150, and 50, the number here, 50, and 150 minus 50. But if we give you the magnetic field like this, so minus 1.5, so and H0R is 0.5. So how we can find it? So to find the reflection standing wave ratio, so you have to write 1.5 plus zero point 0.5, then 1.5 minus zero point 0.5. So we don't see the sign here, just the number, and then sum them. Uh, so the uh, numerator will be sum of this, and, no, and denominator will be the difference between this. So SWR is ES1 max over ES1 minimum, or SS1 max or SS1 minimum, 1 plus gamma, 1 minus gamma. So here this is the formula for finding the standing wave ratio. Now if you have expression like 150 this, negative 50 this, as I showed before, this reflection standing wave ratio will be 2, or you can find gamma equal to this 1/3, and SWR is 1 plus gamma and 1 minus gamma. So 1 plus, so if you see the expression here, right, we got 1 plus amplitude of gamma, 1 minus amplitude of gamma. So this is the SWR formula. So this. Similarly, for magnetic field, you can find the SWR using SS or maximum, minimum, or using the reflection coefficient. So SWR value in medium 1, where both incident reflected wave exist, SWR should be higher than 1 and up to infinity. In medium 2, where we have only one transmitted wave, there will be no SWR, no standing wave ratio, because a standing wave requires at least two waves in opposite directions. But at the transmitted region, we don't have two waves, we have only one wave. So the in medium 2, the standing wave ratio will be 1. So standing wave ratio varies between 1 to infinity. No reflection, meaning SWR equal to 1. 100% reflection means SWR equal to infinity. Now this is how we can find the total wave. We already showed you to find the total wave like this. So you can find the total wave. Total wave is the sum of incident and reflected wave. Then we have to find the location for maximum and minimum in E and S field. So here we can show how to find the location of maximum and minimum. So let us think we have E as 1 equal to E0 I 1 plus gamma E0 2 beta z. So I am assuming this is entire thing is the magnitude and this is the propagation part. So we will get maximum value for this when this value will be positive 1, because we have 1 plus gamma. If you would assume this value is plus 1, then the entire thing will be positive. So if you assume this value is plus 1, that means e to the power z 2 beta z is 1, and 2 beta z is 1, meaning is e to the power 2 n pi, right? 2 pi or 2 n pi will gives you 1. So because 1 means cosine 0 or cosine 2 pi, 4 pi, 6 pi, like this. So if you equate this one, you will get z equal to n pi over beta, or beta equal to 2 pi over lambda, or you can write n lambda over 2. And here n equal to 0, 1, 2, 3, like this. So the maximum will occur at 0. If you put n equal to 0, then it will be 0. N equal to 1, that will be lambda over 2, lambda over lambda, 3 lambda over 2. So if you look at the standing wave, the standing wave frequency will be double to the incident or reflected wave. So that means if you want to find the wavelength of a wave, that is equal to the 2 times the distance between two minimums. Similarly, the electric field will be minimum when this value will be negative 1. So say negative 1, and negative 1 will be cosine uh, 2n plus 1. So that means 100 pi, 270 pi, like this, 180 pi. So we use this formula and we can find this one. So lambda over 4, 3 lambda over 4, 5 lambda over 4 gives you the uh, location for minimum. And everything is measured in negative z-axis because you know the location of maximum and minimum. The standing wave is traveling in not traveling, a standing wave form in medium 1 and medium 1 is has z equal to less than 0. That's why uh, you will get the location for minimum and maximum at for negative z values So we can also find the minimum H field. So you see this is the electric field expression, this will be the magnetic field expression. So electric field expression got a plus here, magnetic field got minus here. So if as it is minus, so you'll get maximum if this value is negative 1 because negative 1 and this minus becomes plus, positive gamma. So this value should be negative 1 to get a maximum. And to get a minimum, this value will be positive 1. So for H field will be minimum when it is positive 1 and you got this thing. And S field will be maximum when this is negative 1, you got this field. And now if you inspect the values you got here, you can see when E field is maximum, S field will be minimum. And when E field is got its minimum, then S field is maximum. So that's how the wave travels. Like electric field is maximum, magnetic field will be 0, and then magnetic field will be maximum, electric field will be 0. So now the input impedance. So we have learned about wave impedance. Now we will be learning about a new type of impedance that called the input impedance. And this input impedance basically measured with respect to the total wave. As you know, the incident electric field over incident magnetic field gives you the wave impedance for eta 1. You can use the reflected electric field or reflected magnetic field also eta 1 because incident reflected both are in medium 1 but at eta 2 for transmitted electric field and magnetic field. But the input impedance, if you take the total electric field over total magnetic field, the ratio is called input impedance. So now input impedance, we can find it like this. So let's say we have the total electric field equation and this is the total magnetic field equation. Now at z equal to a negative L, we put z equal to negative L in this equation and this equation here we come up with this. And now if you replace this transmission reflection coefficient with this formula, you will get the input impedance, got an expression like this. Input impedance eta 1, eta in equal to eta 1, eta 2 plus j eta 1 times beta L, eta 1 plus j eta 2 tan beta 1 L. This is the graph for tan beta L. So you see the tan beta L graph is like this. So it goes from negative infinity to positive infinity, negative infinity to positive infinity as you varies the length or L. So if you varies the length, then you see the input impedance will vary like this. So input impedance will not be constant, like unlike the wave impedance. Wave impedance is constant always, but input impedance is not constant. Input impedance is a function of eta 2, eta 1, and also the function of the length of this. So that means if you measure Z input impedance at this point, it will be completely different if you measure the input impedance at some point here. So if you measure input impedance at different positions, you will get different values. And these values virtually could be anything between negative infinity to positive. So you can have any, can produce any impedance of negative infinity to positive infinity by varying the value for L or by setting the value for L, you can get any value for the input impedance. Now we can use the reflection concept for uh, to get some conditions matching, for example, for matched load condition. So we can check some conditions. So for matched load, you see the condition of matching means eta 2 equal to eta 1. If you have eta 2 and eta, no, eta 1 are same, then the reflection will be 0, transmission will be 1, eta input will be eta 1 or eta 2. So you see here, no reflection will take place if the load is matched, that means impedance are same. If two mediums has the same wave impedance, there will be no reflection there. 100% signals will be transmitted. The input impedance, as you know, there is no input impedance either because it will be eta 1 and eta 2. If 100% signal is transmitted, there will be no reflection and no standing wave. So standing wave ratio is 1. So no reflection, 100% will be transmitted. Now other condition is short circuit. So if you have one medium and another medium is short circuited, then what will happen? So if short circuited means perfectly conducting. That means eta 2 equal to 0. So if you put eta 2 equal to 0, you got reflection equal to negative 1, transmission equal to 0. So if you have a conductor, thick conductor, then all the signals will be reflected back. No signals will be transmitted through the conductor. And the input impedance, you will get the equation like this. So if you put eta 2 equal to 0, eta 2 equal to 0, it will be J eta n1 over n1. So if you cancel n1 and n1, you will get J n1 tan beta 1 L. So that means you can produce any impedance of say capacity for inductive impedance, not resistive impedance. As we have J term, that means it should be inductive or capacitive. If J is positive, then the impedance will be inductive. If J is negative, the impedance will be capacitive. So we can produce any value for reactive impedance by setting this value for L. And the standing wave ratio is 1 plus gamma, 1 minus gamma equal to infinity. As gamma equal to negative 1, so this will be 1 plus 1 is 2 and 1 plus minus 1 is 0. That means infinity. The input impedance is inductive or capacitive as L varies. So input impedance is 0 when beta L equal to n pi. L is this. Input impedance will be infinity where beta L equal to this one. So as you know that tan theta is varies from negative infinity to positive infinity. It could be 0, it could be infinity. So if you get put L equal to n pi over 2, sorry, n pi, beta L equal to n pi or L equal to n lambda over 2, then the input impedance will be 0 at that point. So now we can use this concept for antenna protection. So if tan beta 1 L equal to 0, that means beta 1 L equal to n pi L lambda 1 over 2. So input impedance is equal to eta 2. So that is meaning that the input impedance will be the impedance of second medium. Second medium. If you set the length of n lambda over 2, let's say n equal to 1 or 2 or 3. So if n equal to 1 lambda over 2. So if you choose the length of a wire equal to lambda over 2, then the input impedance will be the impedance of eta 2. So let's say if you connect something with this port and set the length of this wire equal to lambda by 2, then the impedance at that point connected here, let's say this is eta 2 and this side is the input impedance eta in. So here is eta in and here is eta 2. So eta in will be eta 2. So that means you can protect your device. So this impedance is equal to this impedance. So they are matched and no reflection will take place because the impedance here and here are same. So this can be used for antenna protection. So if you want to protect your transmitting or receiving antenna, you can use a cable like this and connect your TV with this antenna like this. So one side is antenna here, the impedance of the antenna will be equal to this. So which is a shift for this. So you can find the overall reflection will be zero because input impedance and the eta 2 is eta 1 minus eta 2. So the overall impedance will be zero. Then another thing is anti-reflection coating. If you see tan beta 1L equal to infinity, so tan beta 1L 2n plus 1 pi over 2, so you can learn n pi over 2. So input impedance is this, input impedance n square over n2. And we can use this concept to make the system reflection free or anti-reflection coating. So let's eta in is eta naught in air, eta 2 in glass, and eta 1 in coating. So let's say this is your air, glass, and coating. So we use this coating on the glass surface to make the system reflection free. So then this is the impedance for the air, this is the impedance for the glass, and this is the coating impedance. So you have to choose the coating impedance is the square root of eta 1 minus eta 2. So that's the geometric mean of the two impedance of these two mediums. So just this the graded system, right? So if you goes from this impedance to this impedance, there would be a reflection might take place because of the impedance mismatch. Now you can use a coating. The coating impedance will be somewhat in between these two. You can use this formula to find the impedance of the coating material. So this is the application for anti-reflection coating. Let's say this glass has the anti-reflection reflective coating, and but this glass has no, it is not coated with the anti-reflecting material. So you see the light wave is reflecting from here. You can see the light wave is reflected from this glasses tube. So how we can make the system reflection free here. So the concept is, let's say this is the incident wave, this is the incident wave, and this is the reflected signal. So this is the reflected signal. So we have incident wave and this is the reflected one. So let's assume another wave is incident here and going to there, and then it will be reflected. So now if you look at this reflection and this reflection, they are completely opposite. So this is positive and is negative. So here and here. So these two waves are 100% out of phase, right? One is coming from here and another one, let's say another wave is coming here and reflected in this way. So these two waves will be cancelled out. One wave that is reflected from this surface and another wave that is reflected from the glass surface. So we have air here and this is the coating substance, air coating interface. So reflection takes place from here and another reflection takes place at glass and coating interface, and they are out of phase, so you will get the medium reflection free. So or this light, if someone see this ray, someone look at this glass, you will not find any reflection because these reflected signals are cancelling out. So for, as you know how to find the impedance of this, so impedance of this will be impedance of this media times this media and the square root of them. So you have to say the eta 1 and this is eta 2. So eta 1 times eta 2 is square root. So square root of eta 1 times eta 2, that's the reflection this. And what will be the thickness of this? So thickness of this will be lambda over 4 because so here it should be lambda over 4. You see the things explained here. So one wave is going this way here. So one reflection will take place at that point and the reflection will be take place at that point. So we need to make 100-degree out of phase. So if you want to make 100-degree out of phase, so that means you have to go half. So this wave and this wave. So you see here where it release from here, it will go extra quarter and quarter half. So that means 90 degrees and 90 degrees. So it will be 180 degrees out of phase. So the signals that reflected from here, let's say this is 0 degree out of phase, and the signal that is traveling here, the lambda over 2. So this is lambda over 4, that means 90 degrees, and again lambda over 4, that will be 90 degrees. So 180 degrees. So that is 180-degree out of phase. So that's why we may have to make it lambda over 4. The thickness of the coating will be lambda over 4. So anti-reflecting coating. So here you see, sometimes we might ask you to find the permittivity of the anti-reflecting coating substance. And we need to find the thickness of the coating. So thickness of the coating will be lambda over 4. And you can find the reflection coefficient by sorry, relative permittivity by using this formula. Okay, so this will be a question like this, or question here, and assume a non-magnetic looking glass has a relative permittivity ER equal to 16. The wave impedance, wavelength, minimum thickness, and relative permittivity of non-magnetic anti-reflecting coating at 300 gigahertz signal. So the wave impedance is here 120. Wave impedance is glass 16, so it will be 30. And therefore, the impedance of the coating will be 120 times 30 square root, so 60. Now, the relative permittivity of the coating will be square root of the glass, so that will be 4. Now, the phase constant on the coating will be beta omega 0 epsilon r 4, so 2000. Wavelength will be 2 pi over beta. This, so thickness will be lambda over 4. So lambda is this. So lambda over 4 is 0.785. 0.785 millimeter.